So today I'm going to talk about exceptions. So you've already got a lot of familiarity with exceptions because Java's been throwing a lot of runtime errors when you try to get your code to work. So today we're going to learn what exceptions really are and how Java sees them. So as you know, when a runtime error occurs in Java, Java prints a very obnoxious error message to tell you what you're doing wrong, and officially we refer to this process as Java throwing an exception. Which usually causes it to print an error message and quit. But interestingly, an exception is more than an obnoxious behavior. An exception is an object in Java, and you can actually catch that object and stop your program from crashing when something goes wrong. So an exception is really an exception object with a capital E. And again, you can prevent the error message by catching the exception. Now, you don't necessarily always want to do this. If you have a class cast exception or an array index out of bounds exception, you probably just want to get your error message so that you know you've done something wrong. But there are times when you do want to catch exceptions. So let's look at a few examples of when it's good to catch exceptions. Exceptions let you cope with lots of different errors that might come up. And they're not just errors like class cast exceptions or null pointer exceptions. They're errors that may happen because your computer is interacting with the real world. So you're reading files from a disk. Sometimes the file's not there. Sometimes the disk is broken. You're reading stuff off the network. Sometimes the network is down. You can't get to your internet connection. You can't read the web page you want to read. And so having error handlers that handle these unusual events, especially when you're doing I/O, is really important. And so here's a typical way to deal with file I/O in Java. We're going to use what's called a try clause. And the idea of a try clause in Java is that we're going to run some statements, but we're going to have error handlers for if those statements throw certain kinds of exceptions. So let's start by opening a new file. So we're going to open a file. We're going to try to read stuff out of that file. The problem with this is that that file has protections that don't allow you to read it. Therefore, when you try to open the file, it's going to fail. And when it fails by throwing an exception, file not found exception. So now what we're going to do is we're going to write error handlers, which we put in what are called catch clauses. These catches are part of that try clause. So the try catch are linked together. They're not separate things in Java. You can't have catch clauses without a try clause in front of them. What the catch clauses do is they give you ways to handle the exceptions that might be thrown by the code in the try clause and deal with them without crashing the code. Now, several things to note about this code is, first of all, each catch clause declares a particular type of exception and then a variable name. And those variable names really are variable declarations. So for the first exception here, I am declaring a variable named E1 of static type file not found exception. And for the second catch clause, I'm declaring another variable, E2, of static type IO exception. And both of those are subclasses of exception. The Java standard libraries have many, many built-in subclasses of exception to handle all kinds of things that can go wrong. And then the code inside the catch clause is called exception handlers. So an exception handler is code that tells Java what you want to do if an exception gets thrown in order to take care of the problems that just arose. So one interesting thing about this code is that file not found exception is a subclass of IO exception. So if you throw a file not found exception, it's actually going to match two of those catch clauses. So let's talk about what this code does. So the first thing this code does is it executes the code inside the try. So inside the try clause. And if all goes well, that code works and doesn't throw any exceptions, and we're happy. And if that happens, then the Java skips the catch clauses. Java doesn't even look at the catch clauses if an exception doesn't get thrown in the try clause. Sorry, talk louder. You're saying if an exception occurs during the try code? Uh-huh. No. No. So, well, that's where I'm going next, which is what happens if the try code throws an exception? So, first of all, whatever the rest of the try clause is, Java's not going to finish it. So we do not finish the try code. We stop wherever the exception got thrown. Instead, what Java does is Java jumps out of that try clause and jumps to the first catch clause that matches the exception. And it executes the code inside that catch clause. And so what do I mean by matches? So the exception that got thrown is an actual Java object with an actual dynamic type, like file not found exception. Java is looking for the first catch clause that declares a static type of exception that is either the same class or a superclass of the actual object that got thrown. So again, what do I mean by matches? It means the exception object that's thrown is the same class or a superclass of the static type listed in the catch clause. Or to put it another way, if it's legal for Java to assign that object to a variable of that static type, then Java does it. And whichever is the first matching clause, that's the one that gets chosen. So to give an example of that, I told you before that file not found exception is actually a subclass of IO exception. So if I throw a file not found exception, it actually matches both catch clauses, but only the first one gets executed. On the other hand, if Java throws an IO exception that's not a file not found exception, then the second catch clause is the one that will get executed. Question? Oh, what's that? Oh, did I get that wrong? Yeah, you're right. Sorry. Wrote down the wrong thing, so please correct that. So a typical thing that would go wrong here is that when Java tries to open the file, if the file's not found, then we're going to go to the first catch clause. And in this case, what catching the exception is going to do is, first of all, we're going to actually print the exception. Exceptions have a toString method, just like most classes. And so you can actually print out what the exception is on the screen. And then it stops the program from terminating just because the file didn't open. And then you can go on and continue executing the code after all of the catch clauses. Another thing that might happen is that Java might successfully open the file with the first line, the new file input stream line. But then the next line, f.read, might fail. And the reason it might fail is if you have a track of your disk that's faulty, you might be able to open the file, but you might not actually be able to read the next byte out of the file. If that happens, then we'll go to the second catch clause, and the catch clause closes the file. So exception handlers are often used to do cleanup tasks like closing files so that you don't leave extraneous files open after file reading fails. So questions about this so far? Mm-hmm. So where are we when this happens? Oh, if you had swapped the two catch clauses? Right. So if you swap these two catch clauses, then the file not found exception clause will never, ever be used. Because IO exception is a superclass of file not found exception. If you swap these two, anyone that would go into the second exception handler will also go into the first exception handler. Java always picks the first one that matches, so then the second one would never get used. Uh-huh. If the try block throws an exception that's not handled by any of these, then the exception happens. So you don't have to catch every exception, and this doesn't catch every exception. If the try block throws, for instance, a null pointer exception, neither of these catch clauses are going to catch it, and the null pointer exception is going to do the same thing it always does, propagate up the stack and cause your program to crash. Back here? Oh, yeah. Yes, if you want, you can just write an exception handler that says catch exception E1. Absolutely. And that'll catch every kind of exception. It's not usually recommended unless you really know what you're doing, because if a null pointer exception happens, you don't necessarily know how to rescue yourself from that. But one place where you would do that is when you're calling somebody else's code, or you're calling some entire sub-application. And if that whole sub-application fails, you don't want to kill the main application. You just want to stop doing whatever you were trying to do in that sub-application. Yes? There are big differences between return and throws, which I'll talk about in a minute when I talk about throws. But I'm not up to throws yet. Yes? If there's an exception happening in a catch clause, generally it is thrown as normal. So the exception handlers might throw exceptions themselves. Those exceptions will not be caught by these lines of code. If the exception handler throws an exception, that just crashes your program as usual. Unless you have another try clause inside the catch clause, which you can have if you want to. Other questions? So again, you don't need a catch clause for every exception that can occur. You can decide that you're going to catch some and handle some, but you're not going to catch others. The second purpose of using exceptions is sometimes you're running a program and your code reaches a point where it realizes that the thing it was trying to do can't be done, and you need to just get out of a bunch of code because the whole purpose of that code has just been defeated. And believe it or not, there are times when you might want to actually roll your own exception and throw your own exception. Because exceptions are the easiest way to get out of a really complicated piece of code whose whole purpose has just been defeated. The classic example of this is parsers. So there's a piece of code called a parser that reads your Java program and then tries to compile it into Java bytecode so that you can run your Java program. The parser needs to read the computer code that you write. And what can happen in parsers is that they're very complicated. They have lots of levels of recursion. They have lots of methods calling other methods with loops at every step of the way. And sometimes you're busy parsing your code, you're deep inside some nested loop, and suddenly you reach the end of the file because the student accidentally deleted the last 50 lines of code. And so now you're in a state where you can't finish parsing because the rest of the code is missing, but you're deep inside a huge nested structure of method calls on the stack. and you need to get out of all those method calls on the stack. That's a case where you might naturally want to throw an exception to get out of all those methods and sub-methods. So here's how you roll your own exception. You pick a name for your exception. I'm going to call mine parser exception. Make it extend exception. And that's it. That's the whole class definition. I didn't add any new methods or any new fields. I didn't add anything to the exception class because I don't really need anything new, but I do need a new name. The whole purpose of a parser exception is to be distinguishable from other exceptions. So I didn't define a parser exception because I need some new capability that other exceptions don't have. I defined a parser exception so that it would be a parser exception, and I can catch it without accidentally catching anybody else's exception. And now that we've got that, let's write some code that throws these. So I'm going to define a method called parseExpression. This parses expressions like x equals y plus z minus h that you might write in your Java code. And it produces a parse tree. But what we care about right now is not what it does under normal working circumstances, but what it does when something goes terribly wrong, which is sometimes it throws a parser exception. And since we're going to write code that can throw a parser exception, we have to declare it. We have to say to Java, this is a method that might throw a parser exception, so be prepared for that. So this bit is required. And I want you to imagine that this is just a really complicated piece of code with lots of nested loops and stuff going on. But at some point deep in the code, there is a check to see if something has gone terribly wrong, like there's no more characters in the file or something like that. And if something does go wrong, then we throw a new parser exception ourselves with the Java throw keyword. So this line of code, throw new parser exception, runs in two steps. First, new parser exception calls the parser exception constructor, and you get an object back. Once you've got that object back, then you can throw it with the throw keyword. So like so many pieces of Java code, this line executes roughly from right to left. First construct the new parser exception, then throw it. So now that we've seen what a throw looks like, you might ask, how is this different from return? Why couldn't we just use the return keyword? There are a couple of reasons. One reason is that, well, we don't have to return anything when we throw an exception. As a matter of fact, we can't return anything when we throw an exception. But the more important difference is that an exception can propagate down the stack through many stack frames. So it not only causes this method to end, but it causes a bunch of other methods below it on the stack to end as well. So you might ask, how many stack frames down the stack is this exception going to propagate? And the answer is, it's either going to keep propagating down until some method catches that exception, or it's going to propagate all the way down right out of main and crash your program with an error message, which, again, you've all seen many times. So once you've got this method, you can have other methods that call it. And just to demonstrate the idea of an exception propagating its way out through multiple methods, here is the method that called parse expression. And while I'm at it, I'll just show you how to declare a method that can throw more than one kind of exception. So in this method, again, this might be really complicated nested loops and complicated code, and somewhere deep inside those nested loops, we have a call to the parse expression method. This method does not catch that exception. So if the parser exception gets thrown, it's going to come out of parse expression. It's going to go right through this method and rip its stack frame off the stack as well and continue down to the next method that called this method. So parse was called by another method called compile. And here I'm actually going to go ahead and catch the exception. And so inside a try clause, we're going to call this method parse that might throw a parser exception. And if it successfully returns something, then we're going to take that parse tree and convert it into bytecode. But if a parser exception gets thrown, we don't want the compiler to just crash. What we want is for the compiler to complain that there's something wrong with your code, I can't compile it, and then go on and try to compile the next file, if there is another file to compile. So we'll go ahead and catch the parser exception. In this example, my exception handler is nothing. I'm not actually going to do anything in my exception handler except catch the exception and stop the program from crashing. And that's always an option, is that sometimes you just want an exception handler that catches the exception and then moves on. So again, the main point here is that we had a sequence of methods on the stack. So there was a stack frame for compile. There was a stack frame for parse. There was a stack frame for parse exception. Sorry, parse expression. And expression parsers are usually recursive, so parse expression might have even called itself. And somewhere in this, in here, we get this exception thrown. And when the parser exception is thrown, it just rips down the stack, tearing stack frames off the stack until it gets caught down here by the compile method. And once it's caught, that exception is actually stored in the variable E1, and now you can go look at it if you want. Any questions about this? Yeah? It's stored on the heap. Yep, just like every other object, exceptions are on the heap. Mm-hmm. Actually, no, you can't declare E1 outside of the try block or outside of the catch. But what you can do is, if you want to have it around afterwards, you can certainly assign it to another variable. Like you can say E equals E1 here, and exception E up here. Pardon me, I guess I put it there. Exception E here. And that will allow you to continue doing stuff with E here. So yeah, you can't declare E1 outside of that catch clause, but you can assign it to another variable so that you still have the exception after the catch clause is over. Uh-huh. Mm-hmm. Mm-hmm. In that case, I did not, and I will explain why next. So, no, I did not have to write throws file IO exception in the first example. I did not have to write throws file not found exception in the first example, and I'll explain why in a couple of minutes. But let me see if there are any other questions first. Yeah. Main can throw exceptions. Mm-hmm. Absolutely. Every method, including main, can throw exceptions. Yes? Oh. I'm not sure I understand your question. Can you say it again, please? Uh-huh. Yeah. Oh, okay. You can throw any subclass of an exception you've declared that you throw. So here, when I said that I throw parser exception, that means I can also throw any subclass of parser exception. So it's not that I can only throw a parser exception. I can throw a parser exception and any subclass of parser exception. Now, the other thing you mentioned was things like null pointer exception and stuff. Those you actually don't have to declare, and I'm about to explain why. So the top-level class of things that you can throw in Java is not called exception, it's called throwable. And throwable is divided into two subclasses. The exception subclass and the error subclass. The exception subclass includes a lot of different exceptions. These are the kinds that you would likely throw yourself. These are the kinds you would likely catch. Things like I/O exceptions, for instance. There's also a very special class of exception called runtime exception. And I'll explain in a minute why it's very special. But runtime exception includes a lot of your least favorite exceptions, the ones that Java throws on you when you don't want it to, like null pointer exceptions, array index out of bounds exceptions, and class cast exceptions. Error, on the other hand, mostly is made up of things that where something really bad happens to the Java compiler that's so critically bad that you probably don't want to catch it. So, for instance, one subclass of error is virtual machine error, which means the virtual machine cannot continue to run for some reason. And a classic example of why that would happen is if it just runs out of memory. And so there's an out-of-memory error for that purpose. One other error that's not a critical machine error, but is in the error class anyway, is the assertion error. Assertion error is what gets thrown when you do the Java assert statement, and the thing that you assert turns out to be false. So if you say assert false in Java, it throws an assertion error. So errors are mostly things that you should not try to catch. If Java throws an out-of-memory error and you catch it, you might succeed in catching it, but it is very unlikely that the Java virtual machine will be able to continue to run if it's out of memory, so all you're going to do is make it crash harder. So errors in general are things you usually should not try to catch. Exceptions are things that you might want to catch for one reason or another. So again, just a few reminders of things I've just said. Catching an error is rarely appropriate. Generally, you want to catch exceptions sometimes, but never errors. And the runtime exception is this special class of things thrown by Java, and usually not by you, not by a library, but thrown by Java while it's actually running and trying to do things for you because you have an array index that's out of bounds or something like that. Now what's interesting is that some of these exceptions are ones that you have to declare with a throws clause if your method might throw them, and some of them are not. And the difference is, well, the ones that you have to declare are called checked. The ones you don't have to declare are called unchecked. And the unchecked ones are these ones I'm circling now. The reason why the unchecked exceptions don't have to be declared is because almost any method could throw them. You never know almost any method could throw a null pointer exception or a class cast exception or an array index out of bounds exception, and it would be a real pain if you had to declare every single method that could potentially throw those exceptions. So Java doesn't make you declare those. Likewise, any Java method can throw an error like an out-of-memory error. You never know when you're going to run out of memory, and it's not something you can control. So Java doesn't make you declare those either. But most of the kinds of exceptions that you would roll yourself, as well as ones that are used by the Java standard library for the same reasons, those are ones that have to be declared explicitly, like I/O exception or parser exception. So all of the exceptions that are not runtime exceptions are checked, which means if you have a method that might throw them, then you have to declare that. And that includes ones that propagate through from some method that you're calling. In other words, when a method calls another method that might throw a checked exception, you have just two choices. The first choice is that the calling method can also declare itself as throws such and such an exception. Or two, you can catch the exception. Generally, the easiest way to figure out which exceptions you have to declare that your method throws is to run the compiler and let the compiler error messages tell you. Any questions about that? Mm-hmm. Yeah, you can. So, for instance, here's an example of, you'll recall we have this compile method which calls this parse expression, this parse method. So the parse method here throws two different exceptions, a parser exception or a dumb code exception. And the compile method calls that method, well, here I have it so it catches the parser exception. What if it didn't catch the dumb code exception? What if it only caught the parser exception? Well, then I don't have to declare the parser exception because I catch it, but I do have to declare the dumb code exception because I don't catch it. Yes? If you extend what? Well, if you extend the runtime exception class, then it will be an unchecked exception. I do not recommend extending the runtime exception class. It's generally considered bad form, but if you do it, it'll be an unchecked exception. Mm-hmm. An I/O exception is a broad class of exceptions that certain Java I/O libraries, input-output libraries, throw when things go wrong. Like you try to read a file, it's not there, or it's protected, or the disk sector is bad, or you try to read the internet and the internet is down when you try to read a web page. Anything that could go wrong when you're doing I/O. All right, we have time for a break, so let's take 5 or so. Now, there's a keyword called finally. So let's give an example of a try clause that has a finally clause at the end. So again, we open a file, we try to do something. I'm not going to be too specific about what the something is. There's just some statement here. I'll call it statement X. And I'll have a catch clause that catches I/O exceptions. And if it catches one, it prints its stack trace. And returns 2. Now at the end here I have what's called a finally clause. A finally clause is something that if the try clause starts to execute, the finally clause will always get executed no matter what. Or at least it will always start to execute no matter what. So I'll say it again. If the try statement starts executing, then no matter what happens, exceptions get thrown or not, the finally clause is going to execute in the end. Or at least it will start to execute. So in this example, I use it to close a file. I want to make sure that that file gets closed in the end, no matter what happens, because I opened it in the beginning, and I want to make sure that whether anything goes wrong or not, that file is going to get closed. Yes, question? If the finally clause itself throws an exception, then it won't finish executing. That exception will get thrown as usual. The first exception gets replaced by the new exception. You can only have one exception. So if an exception is being thrown and a finally clause runs and another exception gets thrown in that finally clause, the new exception replaces the old one. Print stack trace. Well, I'll move that ahead here. So one useful thing to know is that when an exception is thrown, when an exception is created, constructed, it takes a snapshot of the stack at that moment in time. So if you have an exception, if you've caught an exception, you can go look in it, you can go look inside it, and you can see exactly what did the stack look like at the moment that exception was thrown. Or constructed, actually. So coming back to this piece of code, there are a bunch of different things that could happen because the try code may or may not throw an exception. The catch clause may or may not throw an exception itself. The finally clause may or may not throw an exception. So there's lots of tricky possibilities to try to remember. So let's try to see all the different possibilities. So first of all, let's start with the simplest case. What if statement X does not cause an exception? What happens? Well, right after statement X, it says return 1. So I'm going to return 1, but I told you the finally clause is going to execute no matter what happens. So the return statement is not going to stop the finally clause from happening. It's just going to activate it. So when you hit the return statement, okay, now it's time to do the finally clause. And so the finally clause gets executed. We close the file. And then we return 1 as usual. The finally clause is executed, 1 is returned. A second possibility is that statement X causes an I/O exception which gets caught. So in this case, there is a catch clause for I/O exception at the top, and that's going to catch the exception that gets thrown. And then we're going to execute the catch clause. And then, after the catch clause is finished executing, well, I told you the finally clause executes no matter what. So now we're going to execute the finally clause. And if you look in the catch clause, you will see that it ends with return to. Java hasn't forgotten that we're returning to, but you do have to execute the finally clause before we can really return. So the finally clause gets executed, and then 2 is returned. So those are the first 2 possibilities. A third possibility is that the try clause throws some other kind of exception that's not an I/O exception. Well, in that case, there is no catch clause that catches that exception, so the exception doesn't get caught. But the finally clause executes no matter what, so before the exception can go propagating its way down the stack, first we do the finally clause. So the exception is going to keep going on, but we can delay, we can pause the exception to execute that finally code first. Yes? Tricky question. If the finally clause has a return statement, you can, if you're slightly crazy, put a return statement in the finally clause. And so what happens? Do we return 2 or do we return 3? We return 3. So if the finally clause has a return statement, that return value replaces whatever return value we thought we were going to return, which kind of makes it a waste of time to have even bothered to write the other 2 return statements because they're never going to happen. In this example, it would always return 3. Question towards the back? Yeah, you. It finally throws an exception in addition to the exception that was not caught, then the new exception replaces the old exception. So the exception thrown in the finally clause wins. The old exception gets forgotten, dropped on the floor, and the new exception replaces it. Yes, sir? So it would return 1 That's it. When you say return something, that return thing immediately goes into a secret spot where Java puts return values. So Java is not going to go back and look at A again later. Yes? Say that again? There's all the what statements are out? Return statements. All the return statements are outside the cache. All right. Well, if an exception gets thrown and doesn't get caught, there's no return value. So you can, if there's an exception not caught, forget about return values. They don't matter anymore. Other questions? Yeah. It's in the second case. It's f.close is executed after e.print stack trace. Yes. Mm-hmm. That's right. So, to go through a few more possibilities, the catch clause might throw an exception itself. If that happens, you can have an exception in a catch clause. Then we terminate the catch clause immediately. But the finally clause is going to execute, or at least start executing, no matter what happens. So we have to go do the finally clause now. And then, after that, the exception has not actually been caught. The new exception has not been caught. And so that exception continues down the stack. And of course, you can have an exception thrown in a finally clause. So the new exception replaces the old exception, if there was one. As we've just discussed. And the finally clause terminates immediately, and so does the method. And that's why I said you're absolutely guaranteed that the finally clause will start to execute, but you're not guaranteed it'll finish executing because it might throw an exception itself. And lastly, to add one more order of complexity here, inside a catch clause, you can have another try clause that throws and catches its own exceptions. The same is true inside a finally clause. You can catch exceptions that are thrown inside the finally clause by having another nested try clause. I want to talk about the constructors briefly. There's just a convention you should know that almost all throwables follow. Almost all throwables have two constructors. And so you should define them like this. So there's one that takes no parameters. And there's one that takes one parameter in the form of a string. And yes, remember you do have to define both of them explicitly if you want to have them both. If you don't define them explicitly, you only get the zero parameter constructor from the superclass. So the second one just takes in an error message so that there can be an error message stored in the exception. And that error message, if it propagates out of main and your program crashes, then that error message actually gets printed by the Java virtual machine. So it's a good way to just send an error message to the user. And if if the exception is caught, so it doesn't propagate out of main, then you can read it with a method called getMessage. Which is defined in the throwable class. So your program can read and examine that string if you want. Questions about that? Yes? Finally throwing an exception. Right. If the finally clause throws an exception, then that exception will act just like any other exception. Propagate down the stack until somebody catches it. Mm-hmm. Yep. There's nothing special about exceptions thrown in the finally clause. Yes? So I would recommend it. I'm not sure whether the super actually does anything, but if you don't call super, then, well, wait. Oh, no, I guess it's not required. No, I guess if you leave it out, it does the same thing. That's right. Okay. No, it's not required. All right, that's the end of exceptions. I'm going on to a completely different topic now. Java has something called generics, which is a way of taking a data structure that stores objects and making it store a particular class, where you get to pick the class at the last minute. For those of you who have some experience with C++, Java generics are a little bit like C++ templates. They're a little bit different too, but much of the idea is the same. So here's the idea. Suppose you're using some data structure like a list to store strings, and you only want it to store strings. Well, what we do is we want our lists to be general purpose software that can store lots of different kinds of objects. And so we wrote our lists so that they store items of the object class. But if you want to store strings in it, you can store strings in it. But then when you get the string out of the list, it comes with static type object, and you have to cast it back to static type string before you can use it as a string. what would be nice and less error prone is if you could actually say, I want this particular list to only store strings so that I never have to worry that the things that come out of it aren't strings. And so generics give you a way to do that. And generics, therefore, guarantee that you'll never get a class cast exception, because suppose you pull something out of your list, you cast it to string, but it's not really a string, it's really an integer with a capital I. You're going to get a class cast exception. You can avoid that entirely with generics because you can say, I want to construct one copy of this list that can only store strings. Since it can only store strings, you'll only ever get strings out of it. So what generics do is they allow you to declare general classes, meaning a class that can store any type of object, and then use those classes to produce specialized objects, like a list that can only store strings. Let me repeat that. I'm going to declare a general class, a class that can store any kind of object in my list. But I'm going to be able to produce a specialized list that only stores strings, and another specialized list that only stores integers, and another specialized list that only stores exceptions. So what that means is I'm going to be able to construct an S-list for strings. No one will ever be able to put an integer into my S-list for strings. And no one will ever be able to put a string into my S-list for integers. But both of those S-list objects came from the same single S-list class. I only had to write the S-list class once, but now I have an S-list for strings, an S-list for integers, an S-list for exceptions, S-list for any other object I want. To make that work, Java generics allow you to define classes that take what's called a type parameter. A type parameter is kind of like a parameter that you pass to a method, but you're passing in a type. So I define a class that has a type parameter, and then later when I want to construct an object of that class, I pass in the specific type of thing I want those lists to store. So here I'm going to write you an S-list method that can store any type you want. Here T is the type parameter, and I put it between a less than sign and a greater than sign as sort of brackets that go around type parameters in Java. So I have class S-list node, and this is going to be an S-list node that stores objects of type T, and I get to decide what type T is later on when I actually construct the S-list. So I know I want to store objects of type T in this list, so I'm going to declare item to be of type T. And then I'm going to need S-list nodes to have a next field that points at the next S-list node. And I'm going to say the next S-list node in the list is going to store the same type as this S-list node does. And I'm going to have a constructor in my S-list node class. And my constructor will take an item, and what is the type of that item? It's type T. And it will take an S-list node, but the type of that S-list node is S-list node T. It has to be an S-list node that only stores type T. So there's my slist node class with a type parameter. And now if I want to create an slist node that can only store strings or an slist node that can only store exceptions, I can do that. So now I want an slist as well. So I'm going to do the same thing. I'm going to have a class of slists that only store things of type T. And with that, for now, I'll just give that a head field. Let's forget about the size field for now. But the type of the head is slist node T. And I'm going to need methods like an insert front method. And my insert front method takes an item that I want to insert into the list. And what does the type of that item have to be? It has to be type T. And so insert front will work just by constructing a new slist node T that goes at the beginning of the list. And then I update the head field for the new head of the list. So there you go. That is a semi-complete slist class that has a parameterized type. So now I want to use this. I want to actually construct an slist node that only stores, say, strings. So an slist that only stores strings. So how do I do that? Well, now I don't use T anymore. I need to actually fill in an actual parameter that fills in the formal value of T. So I want strings, and so I'm going to declare a variable whose type is an slist of strings. And having declared that variable, I'm going to construct a new slist of strings. So here I'm constructing the actual object and storing it in that variable. And now that I've done that, I can insert a string into it. Now, when I said string here, I am passing in an actual parameter to fill in for the formal parameter T in the slist class. So that is the actual type parameter. I hope you all remember from 61A or whatever previous class you took the difference between actual parameters and formal parameters. But that's the actual parameter. And of course, the formal parameter is here in the slist class. So what's happening when we actually construct an slist or declare an slist variable is that now we are substituting the actual type parameter for the formal type parameter in the slist class. And so all of these T's magically turn into string. Oh, and the other thing that can be handy here is that now I can take an item from the front of the list if I have the right methods to do that, and I don't need a cast. The item method is not going to return static type object, it's going to return static type string. So questions about this? If you try to insert something that's not a string, you will get a compile time error. And in fact, that's one of the bonuses of doing this, is the fact that Java is checking for you when you compile the code that you can only put strings into this thing. And if you try to put something that's not a string in, you find out when you try to compile the code, instead of finding out when you try to run the code and get a class cast exception and wonder, why the hell am I getting a class cast exception? So it's really doing you a favor by doing the checking up front, so when you first make the mistake, it catches your error. Yes? Why do you need the 2 brackets after item? Well, do you need the 2 brackets after item? Let's go see. Well, I didn't make item public. If I'd made item public, I wouldn't need a method. But since I didn't make item public, I'm decided that there should be a helper, or a public method that gets the item field for me. You could do it either way. It's up to you how you design your S-list. You can have more than one type parameter. Yes. I'm not sure I remember the syntax, but I think you could do something like, here, you could do something like S-list TU, but I'd have to double check what the notation is. I don't use it often enough to remember. Other questions? Yeah, back here. Oh, do you mean the actual object that I insert? The object that I insert absolutely can be a subclass of string. So suppose you had a subclass of string named substring. Then yeah, you can insert that into this list. So this is not just a list of strings. It's a list of strings and all their subclasses. And if I make a list of exceptions, that's a list of exceptions and all their many, many, many subclasses. Yes? Well, the letter you choose doesn't matter except insofar as this is what defines the formal parameter. So if I had made this a W, then this would have to be a W and this would have to be a W. But this could still be a T. Does that answer your question? Other questions? Pretty much, yeah. Just have some what? For the most part, yeah. You can pretty much always treat a subclass as if it were the superclass in most contexts. There are exceptions to that rule, but they're kind of too obscure to go into right now. Yes? You're saying when you say leave the S-list node class as it is, do you mean as it originally was? As it is there, or? Mm-hmm. Then, okay, if the S-list node class doesn't have the formal type parameter, then you would have to do your casting inside the S-list class. Like, suppose that Suppose that I made my slist node so that item is still object. Well, now every time you want to pull that item out and give it to somebody, you have to cast it back to string. So who would do that? Well, the slist class would probably do that. Like you'd have a public method item. And then it would be the item method's job to cast to type T whatever the item field is. Does that make sense? Is there another question? All right, so now that we've talked about this, I want to talk about the advantages. Why is this worth going to the trouble to do this? You get rid of some casts, but you add some other cruft in your class that you didn't have before. So it doesn't necessarily make your code look any cleaner just because you're getting rid of some casts. But the big advantage is that the compiler ensures at compile time that nothing but strings can get into your list. So one reason that's useful is it's just good policing. If you want to have a list of strings, it's good to make sure that nothing that's not a string can get into it. But an even more important reason is that it makes debugging a lot easier, because if, under the old system where we just had lists of objects, if you accidentally put an integer into your list of strings, then what would happen is eventually you'd get that integer out, you'd cast it to a string, and you'd get a class cast exception. And then you'd have to figure out how your bug got into the code. And eventually you'd realize that, oh, there's an integer in my slist. How did that get there? And then you'd have to go back through all your other code and try to figure out where on earth did that integer come from? How did it get into my slist? Now, Java makes sure that that integer can't get into your slist in the first place. It'll give you a compiler error message when you try to put an integer in, and already at that point you know what's going wrong, what the source of the error is. So I only have time to just scratch the surface of Java generics today. They're actually a pretty complicated subject. There's a good tutorial online, and if you want to see that tutorial, the URL to download it is in the lecture notes that'll be available afterwards. The other thing I want to mention is, again, because probably some of you are familiar with C++ templates, what is the difference between Java generics and C++ templates? The most important difference is that in C++, when you have generics, they are recompiled for every different type. So if you have a list of strings and a list of integers and a list of something else, Java will recompile them for different types. C++ will do different versions for different types and have a separate object library for each different type you invoke. That can be good for optimization, because it means sometimes the compiler can do optimizations that make it very fast. On the other hand, it also makes your code blow up, because you may wind up with 20 different versions of the same slist class. One for strings, one for ints, one for this, one for that. In Java, there is only one version of bytecode for the slist class, and that one version of the bytecode works on all different types of objects. So that's kind of a trade-off between optimization and code space. The other thing is that in C++, you can use primitive types for the type parameter. In Java, you cannot. So I cannot have an slist of primitive ints. I cannot have an slist of primitive chars. In C++, you could do that with templates. But in Java, generics are only for objects. I want to talk briefly about the ugly topic of field shadowing. And I was sorry to see on Piazza that many of you were torturing yourselves by trying to learn this before the midterm. Field shadowing is something that sort of looks superficially like method overriding, but it has completely different rules and therefore is very confusing. So, just as methods can be overridden in subclasses, fields can be shadowed. In subclasses. But shadowing is very different from overriding and a lot less useful. So this is something you need to know about, but it's not something that's going to be a useful part of your life. It's more something you need to know to avoid pain. So in overriding, the choice of methods is dictated by the dynamic type of the object. But in field shadowing, the choice of fields is dictated by the static type. So let's see some code that does some of this stuff. All right, so here we've got a superclass and its subclass. And in the subclass, we have a field called X, which shadows the field called X in the superclass. And we've got a method called F that overrides the method called F in the superclass. So what's going to happen now is that any object of the subclass actually contains two different fields called X, which is very confusing. But they're really both there. So if I construct a sub-object, like that, well, here's my object. It's got two different fields called X. To distinguish them, I'm going to call one of them sub.x, and I'm going to call one of them super.x. And, of course, every sub is a super, so I can always declare a super type variable, sup, and assign it the same object. So now I've got two different references to that same object. But those two different references have two different static types. And of course, these have been initialized so that the superclass X is 2 and the subclass X is 4. Because that's what the initializers in these classes do. And so now, let's throw in an int here so that I can start probing these values. If I write what is soup.x, then, well, the static type of soup is the superclass. It only knows about the superclass X. It doesn't know about the subclass X. So, not surprisingly, that's going to return a 2. If I write I equals sub.x, well, sub has a different static type. It has the static type of the subclass. And so it's going to look at the subclass version of X, because the subclass version of X is shadowing the superclass version, essentially hiding it. And so we're going to get a 4. Now, if I want to examine the other X, I can always do so by casting. I use a cast to change the static type, and then I look up X, and then I get the X that's appropriate for the static type I cast to. So if I write I equals cast sub to a super, and then, after casting it, take X, then I'm going to get a 2. I can do it the other way around. I can take soup and cast it to the subtype. And Java uses the static type sub to decide which X it should return. So I get 4. I want to compare this with method overriding. What happens if I do this same kind of stuff for method overriding? Well, if I call soup.f, well, always, Java does dynamic method lookup. So it's going to look at that object and say, is that object a sub or a super? It's a sub, so we use the appropriate method call in the subclass, this one here, and we return a 4. And if I say I equals sub.f, Java does dynamic method lookup again, and the dynamic type hasn't changed. It's still a subclass. We still get a 4. And I can try casting it to the superclass. If I cast it to the superclass, will I get the superclass method? Well, no, I won't. Java just does dynamic method lookup and says, oh, it's a subclass. So it just doesn't matter what I do with the static type of this variable. It's always going to do dynamic method lookup, and so I'm always going to get 4. Coming back to the left-hand side, field shadowing, sometimes the variable that you want to work with is this. And so if it's this, then this works the same way. Let's suppose that we have in the subclass another method. So in here, in the subclass, I'm going to have a method g. And g looks like this. If I say I equals this dot x, and this g is being called on a subclass object, so this has static type of the subclass, and I'm going to get a 4. But what if I want the superclass x and I don't want the subclass x? There are two ways I could get the superclass x instead. One is I can do a cast as usual. And that'll give me the superclass field. The other thing I can do is I can actually use the super keyword. The static type of super is the superclass. So if I say I equals super.x, That will also give me the superclass value, which is 2. So that's how shadowing works. But now that you know how it works, whereas method overriding is a powerful benefit of object orientation, method shadowing is just largely a nuisance. Not a method. Wherever possible, avoid having subclasses that have fields with the same name as their superclasses. The reason why you need to know about shadowing is because it does come up in real software, especially when you have a situation where your program is using somebody else's class and some other person's class, and both people used the same variable name or the same field name in their respective classes, and you want to take stuff from both of them, or especially from different interfaces. So that's the main place where you have to deal with shadowing, and therefore you need to know about it to be a useful programmer, but it's not something that's useful. It's not something you want to create. You don't want situations where you introduce shadowing into your code unnecessarily. It's also worth knowing that what applies to fields also applies to static methods. Static methods do not have overriding. Static methods follow the same shadowing methods as shadowing rules, the same shadowing rules as fields do. And you might ask, why? Why don't static methods override? To override, you need to have dynamic method lookup. To have dynamic method lookup, you have to actually have an object to call your method on. But static methods have no object. That's the whole point of static methods. There's no object to do dynamic method lookup on. Therefore, you can't override. You can't do anything other than shadowing rules. I have one last 30-second topic, which are the final keyword can be applied to methods and classes, not just variables. So what is a final method? A final method is one that cannot be overridden. And what is a final class? A final class is one that cannot be extended. You can't make subclasses. If you try to do either of these things, you will get a compile time error. And why would you have final methods and classes? The answer is sometimes if Java knows that a certain method cannot be overridden or a certain class cannot be extended, then it can optimize and make method calls a little bit faster. Especially if there's a method where Java knows there will never be a need for dynamic method lookup because there's no possibility of overriding this method, then Java can do that method call faster. So that's the only reason to do that. And I'll see you on Monday. And thank you.